So our last section in the electron transport oxidative phosphorylation chapter kind of deals with putting these two pieces together and then also thinking about how we regulate this process. And then we'll have a few kind of applications at the end talking about kind of the dangers of oxidative metabolism. So to introduce this concept of the PO ratio, and this is again how they got some of the new numbers for kind of what FADH2 and NADH are worth. The idea is that the amount of ATP synthesized, which refers to the P number, is going to be directly related to the amount of oxygen that's used in the electron transport chain. And with the connection of these two, that allows us to think about this PO ratio, that ATP synthesis requires this proton gradient, and that we're not going to dissipate the proton gradient without synthesizing ATP. So these are connected. And again, we have a little asterisk there saying generally, because we know about things like the diet drug 2,4-dinitrophenol, as well as uncoupling proteins that help us to disconnect electron transport with, and the generation of that proton gradient with oxidative phosphorylation and the synthesis of ATP. So not going to spend a lot of time on this even in class because these are concepts we've talked about before, just kind of seeing their application here. So again, with uncoupling proteins and then diet pills like 2,4-dinitrophenol, those are alternative ways of discharging that proton gradient. So what we are going to spend the most of the time focusing on with this last section here is how we regulate this. And I'm just going to give a brief overview here because we'll get into some of the details and some of the math that we see here in our activities in class. But just to point out, I think this is kind of a neat story to point out that kind of a woman and kind of what she needs in terms of a daily caloric intake kind of relates to about 100 kilograms per day of ATP being used. Now that's like 220 pounds of ATP. There's not even that much woman that's there, right? So the idea is that we need to recycle this. So obviously we recycle ATP by taking the spent ADP and PI, moving it into the mitochondrion, regenerating ATP and putting it back out. So that process that we learned about with electron transport and oxidative phosphorylation is key to this. So again, thinking about how we regulate that is important. We'll go through the details of this in class and with our activity, but remember that there are 4 complexes that we see in electron transport, 3 that really contribute to a proton gradient, and thinking about moving through cytochrome C in all the way through complex 3, that is highly reversible. So those are near equilibrium reactions, so not good control points. We don't get to something that's far equilibrium until we get to kind of cytochrome C, which moves electrons between complex 3 and complex 4. So we'll kind of talk about that, but that's why we have the title of this slide. It's all about cytochrome C. It's how much of that hydrophilic mobile carrier is in its reduced form. That determines the extent of flux through the electron transport chain. So again, if there's lots of cytochrome C in its reduced form, that's going to be an activator of electron transport to allow us to kind of go through that process. And similarly, if there's not a lot, we're going to have low flux through electron transport. And so the amount of cytochrome C that's in its reduced state is indirectly related to the concentrations of NADH and ATP. And this is something we'll spend some time in class kind of going over. 2 kind of fractions that we talked about. One that relates ATP with its hydrolysis products, and set up in this way as we see on the right here. This is what we call the ATP mass action ratio. So sometimes we'll refer to that. And again, this is a direct indicator of whether we're in kind of a need state or a fed state. And similarly, we can think about the ratio of NADH and NAD plus, determining whether we're kind of in a need state or a fed state. And we've talked about specifically this sort of ratio and this sort of ratio indirectly when we just talked about whether these substances are activators or inhibitors of parts of glycolysis or parts of the citric acid cycle. So we'll revisit that at the end. Not going to spend a lot of time on the details of this. We'll get through that with questions and a very directed activity. So again, all about cytochrome C. And so we'll kind of always make sure to go through our logic check and make sure that these things make sense for us. One other kind of piece to put in here is a really neat protein called IF1, which stands for the inhibitor of the F1 domain of complex 5, our ATP synthase. And so what's kind of cool is this is a pH-sensitive protein that will serve to activate or inhibit that ATP synthase domain of, or the ATP synthesizing domain of ATP synthase. Remember, there's the F1 domain, which is that lollipop head that's responsible for synthesizing ATP, and then there's the F0 domain, which that's responsible for translocating protons. And so what we'll talk about here is how this pH-sensitive protein works. And again, we'll talk about it from two kind of extremes, from a resting state versus an active state. So kind of a neat protein to think about in terms of regulation. Then we'll kind of put it all together, make sure to review things that we've talked about before. So that's why we have this figure at the very end of the chapter, which talks about how we have all kinds of feedback inhibition to talk to important players in glycolysis, as well as the citric acid cycle. Again, here we can see in this figure here, this NADH to NAD plus ratio, and kind of indirectly we see the ATP and PI here kind of helping to regulate through that ATP mass action ratio. So we'll take some time in our activity and review and map on all the way through, because once we've learned glycolysis, the citric acid cycle, and then electron transport oxidative phosphorylation, those three metabolic pathways really comprise the heart of metabolism. When we learn about the metabolism of fats, the metabolism of proteins, we really just learn where they feed into this central kind of trunk of three metabolic pathways. And then the last little thing to just kind of talk about here, and we'll have a couple case studies that we can consider looking at, is thinking about kind of the downsides of aerobic metabolism, right? So aerobic metabolism is very good because it's efficient, but compared to what we see in terms of the anaerobic glycolytic pathways, right? That's very rapid, but also very inefficient because we have a fuel here that we really haven't fully squeezed all of the energy out of. So we do make some ATP, it happens very quickly, but it's not sustainable in terms of long term. So that's why we have aerobic metabolism, up to 16 times more efficient by making 32 ATP, but we've already talked about the fact that it's much slower, and beyond that, some things that we haven't talked about, it's not without its costs. So we'll kind of talk about some of the consequences and the costs of not only having oxidative chemistry happening, but the damage that can cause if you disrupt and you eliminate oxygen flow. And so we'll talk about things like myocardial infarctions or any cerebrovascular accidents like a stroke or something like that, how that impacts this process. So kind of a neat story to think about in terms of the sequence of events that happens with oxygen deprivation. So again, oxygen deprivation can be problematic. So if you're what we call an obligate aerobe, that means you have to have oxygen. You have to, sustain yourself through aerobic metabolic processes. What happens when you deprive yourself of that oxygen? But again, on the flip side of it, if you use oxygen and you generate potentially reactive oxygen species, how can that be problematic? So again, our mitochondria are just exposed to high levels of oxygen, and that allows for the potential production of these reactive oxygen species. So we'll talk about two of them in general. Radical species, one's called the superoxide radical, another one's the hydroxide radical. They're very short-lived species, as we see here, which means they act very locally. Once they diffuse away kind of from their site of origin, they're already kind of destroyed, so we don't have to worry about them, but they're very, very reactive where they're generated. And so some of the things that they can do, I'm not going to spend a lot of time right now talking about them, but in class and with some case studies, we can talk about the kinds of damage that can happen within mitochondria with all of this production of reactive oxygen species. So clearly your body must have some way of kind of taking care of that. And your body has several enzymatic methods, and superoxide dismutase is one of the main ways. So this is also called SOD. This is an enzyme present in nearly all cells, and its purpose is to kind of get rid of these superoxide radicals, these very reactive radicals. And so we'll talk about in the next slide, yes, you basically just kind of convert one evil into a lesser evil, because peroxide is still problematic. And so we still have peroxide that you have to deal with, and so peroxide needs to be disposed of in some way. And so you have a couple of enzymes in your body responsible for that. One of them is catalase. So catalase is responsible for breaking down reactive peroxides into water and molecular oxygen. And again, glutathione that we've talked about is your body's natural antioxidant. And a lot of these enzymes that we'll talk about, they have certain metal ions that they are require for activity, and selenium is one of these that's required kind of in this process. And so that's why selenium is touted as having kind of these antioxidant properties. So that's it kind of for electron transport and oxidative phosphorylation. We'll have some neat case studies that we can look at that look at kind of some applications of this in some really neat settings.